Hello, in this video I'm going to solve the following challenging problem on the topic of definite integrals. Compute the following integral from 0 to 1 ln of 1 plus x over 1 plus x squared dx. This is a problem on the Putnam exam 2005. I would recommend to pause the video at this point and give it a try yourself first. Okay, now let us solve the problem. The first thing I will do is to introduce a variable theta to be tangent inverse of x. Of course, this is not very strange. Whenever you see this combination 1 plus x squared as part of the integrand of your integral, this is a very natural way of thinking. Yes, tangent. So from here, x becomes equal to tangent theta. Yes, and of course because you need dx, so this motivates you to differentiate both sides, but the derivative of tangent theta is secant theta squared d theta. And then what you need to do, because you have introduced a new variable, this will affect your bounds, yes, the lower bound and upper bound. So what you do, you would say that x, my old variable, goes from 0 to 1. Let us see what are the lower limit and upper limit for my new variable theta. If x is 0, when I put here tangent inverse of 0 becomes 0, so this is 0, and if x is 1, tangent inverse of 1 is pi over 4. So if you don't mind, let me call this integral I. So then this integral can be written in this form. Going from 0 to 1, now I go from 0 to pi over 4, and then 1 plus x squared becomes 1 plus tan theta squared, and then I will have ln of 1 plus x, but x is tan theta, and then dx is secant theta squared d theta. Yes? But this is a very famous combination in trigonometry. 1 plus tan theta squared is nothing except secant theta squared, which is very good, because now this secant theta squared in the denominator and this secant squared theta in the numerator are cancelled. My integral becomes equal to, so this means that integral I that I'm looking for can now be viewed trigonometrically in this form. In the beginning, you might think, okay, what is the purpose of doing it? Because I have made my integral not simpler that much. I have changed algebraic integrand to a trigonometric one, and usually trigonometric ones are harder. Okay, but now you see that a miracle happens here. So let me write it here. What we want to do next, we want to introduce a new variable, phi, to be pi over 4 minus theta. You will see why. Okay, but the standard way is just differentiate both sides. So this becomes d phi equals to minus d theta. So the d theta that I need becomes minus d phi. And again, this will affect my limits. So theta goes from 0 to pi over 4. This means that phi goes the other way around. If theta is 0, phi is pi over 4. And if theta is pi over 4, phi is 0. Okay, so this integral I now can be written as integral from pi over 4 to 0 instead of the previous limits. And then this becomes ln of 1 plus tan of theta. But phi is pi over 4 minus theta. So if I move theta to the left and phi to the right, theta becomes pi over 4 minus phi. So I will write it as pi over 4 minus phi. And that is the interesting part. You see that why this will work. Okay, sorry. D theta is minus d phi. So I put a minus sign out. So instead of d theta, I put minus d phi, I put the minus 1 out, and that is very good because now this minus sign can be used to swap these limits. So let me write it like that. So this becomes integral, I will take this minus sign away, and interchange the role of these two. But this one, I can use subtraction formula for tangent. So let me write it here for you. So tangent of two angles, alpha minus beta, can be written as tangent of the first one minus tangent of the second one, divided by 1 plus tangent alpha tangent beta, yes? But now, in this problem, alpha is pi over 4 and beta is 5. So tangent of pi over 4 minus 5 becomes equal to tangent of the first one, which in this case is pi over 4, and we know tangent pi over 4 is just 1, minus tangent of the second one, yes, divided by 1 plus tangent of the first one, which is again 1 multiplied by the tangent of the second one. It's a very nice combination. 1 minus tan phi divided by 1 plus tan phi. So this becomes equal to ln. So I use this minus sign to swap them. ln, I will write this one, but instead of this expression, I write that fraction up there. So 1 minus tan phi divided by 1 plus tan phi, and then d phi. Now you see something very interesting happens here. If I take the common denominator here, what will happen? So let us do it patiently, because this part is very beautiful. So this becomes ln of, I take the common denominator to be 1 plus tan phi. So this will be multiplied here, 1 plus tan phi, plus this has not changed at all. So I have to copy and paste its numerator. And then I have d phi. I hope that you can see what's happening. This tan phi and that tan phi are gone. 1 plus 1 becomes 2. So this becomes integral from 0 to pi over 4 ln of 2 divided by 1 plus tan phi. And everything d phi. Hopefully it is readable. Okay, now what happens, you know that ln of a fraction can be written as ln of the numerator minus ln of the denominator. Okay, so let me write it here. Yes, I am in the frame, correct. So this becomes equal to integral from 0 to pi over 4 ln of the numerator minus ln of the denominator, d phi, and then everything d phi. Okay, so now let us continue. I can decompose my integral to two parts. Integral of the first one minus integral of the second one. So this becomes integral of the first one minus integral of the second one. Okay, so if I ask you what is this one, I hope that you are not confused. Do you remember my integral was called I? By changing this, by introducing this new variable, I rewrote this I in this form. So this is nothing except I. Yes? But this I can go a little bit further, because this one is just a constant, so I pull it out, and integral of d phi just simply becomes phi. I have to run it from 0 to pi over 4. But the interesting thing is that if I ask you what is the value of this integral, it will tell me, of course, I don't know, but I am sure that this integral is exactly equal to the original integral I, because the only difference between this one and that one, you see, the limits are the same, the structure of the integrand is the same. The only thing is that the name theta here is phi, and you know that the integral, the variable of definite integration, is a dummy variable. It means that if you replace theta with any other variable, the result of this will not change. So if I call this I am allowed to call this I again, and this is a minus I. Okay, and now I forgot something, sorry. This ln of 2 is pulled out. I forgot to pull this out. I have to pull this out, and then integral of d phi is phi. I have to run phi from 0 to pi over 4, and then, sorry again, this is I. Okay? So what happens now? I move this I to the other side, so it becomes 2I equals to phi goes from 0 to pi over 4 is just pi over 4, so it becomes pi over 4 ln of 2, but I am looking for I, so I divide both sides by 2. So it becomes pi over 8 ln of 2, and this is the answer to this enigma. I don't know, I really enjoyed solving the problem myself, and I really don't know how the designer of the question came up with this very beautiful and elegant idea. So I also hope that this video was helpful for you and you also enjoyed the solution. Okay, so please write what you think about the problem in the comments. Until the next video, be safe and goodbye. Thank you.